Welcome to the Organic Chemistry video content to accompany the Organic Chemistry Lecture Guide and Organic Chemistry Primer. The practice problems in this video come from Part 1, Structure, Stability, and Conventions. The first part of this problem set deals with acids and bases. In this example, we see three common protonation states for citric acid, and we're asked which protonation state will predominate at a pH of 2, 3, 5, 6, and 7. So how do we approach such a problem? Well, the pKa can be thought of as the pH that must be achieved in order to take off the proton from that species. So with a pKa of 3.3 for this first species, we must meet a pH of 3.3 or higher, more basic, to achieve deprotonation of the majority of that species. The second species has a pKa of 4.5. The pKa 2 indicates the pH you must reach for citric acid to lose 2 protons. So pH above 4.5 indicates a pH at which most of the compound will have at least 2 protons removed. And if you reach the pH of 5.8, corresponding to the pKa 3, or the pH at which the majority of the species has 3 protons lost, you would get all the way to this species in which 3 protons are lost from the citric acid. So for the indicated pHs in A and B, pH of 2 or 3, those pHs are too acidic to remove even the first proton from the citric acid. So you would have a species that looks like this. Once you reach a pH of 5, that's basic enough not only to remove a proton from this species, but also to remove a proton from this species with a pKa of less than 4.5. So at a pH equal to 5, you would actually have a species corresponding to the species in the bottom right, where 2 of the protons have been removed. At a pH of 6 or 7, those are both higher, more basic pHs than the pKa 3. So you would have, for D or E, pH of 6 or 7, a species with all 3 protons removed. The next problem probes our knowledge of how the structure influences the acidity of a particular organic species. If we look at this row of compounds, we're asked to rank the compounds 1 to 4 from most to least acidic, and 1 is going to be our strongest acid. The easiest way to think about this is first identify the proton that will be lost here from the oxygen, and compare the stabilities of the conjugate bases of those acids. In this case, the negative charge is on oxygen in all cases. In 3 of the cases, we have the possibility to stabilize that charge with resonance. A resonance stabilized species is a more stable conjugate base. A more stable conjugate base comes from a stronger acid. So this compound that does not have resonance should be the conjugate base resulting from the weakest acid. For the remaining 3, all of which have resonance stabilization, we have to turn to the inductive effect to figure out whether or not there might be some stabilizing or destabilizing features. In the case of this species, we can draw the OH bond and indicate that there's a very strong partial positive on that H and a partial negative on that O. There could be some hydrogen bonding between the negative charge of the conjugate base and that H of the OH group over here. That's a stabilizing influence. Neither this unit over here nor this unit over here has such a stabilizing influence. So this should be our strongest acid of the series, having the most stabilized conjugate base. Now what about the remaining 2 species? We don't have any attractive forces, so we have to examine the repulsive forces. If you draw all the hydrogens on these carbons here, you can see that we'll start to have some electron-electron repulsion between the negative charge on this oxygen and the electrons making up these bonds. So that's a repulsive force. Here we have 2 small hydrogens. We don't have these big CH3 groups like we do in this species. So that makes this conjugate base less stable. It's harder to make. It's less likely for the acid to lose the proton to make such a species. And our second strongest base would be this first species on the far left. This strategy of looking at the conjugate bases can also be applied to the second row. We compare these 4 to one another by drawing the conjugate bases. And they all have, to some extent, resonance stabilization by merit of having these aromatic rings adjacent to the negative charge. If we draw all the possible resonance contributors for these species, we'll see that one of these species has resonance around the ring, just like all these other compounds, but it also has this NO2 group, this nitro group on the outside, and we can push electrons out to the O. Remember that the larger the space over which you can delocalize the electrons, the more stability you get. This is the most stable conjugate base. It's easiest to form by deprotonation. The easier it is to deprotonate something, the stronger an acid it is. This is our strongest acid in the series. The other three don't have any extra resonance because they don't have substituents onto which we can push the electrons to delocalize them farther. So again, we turn to looking at inductive effects. One of the inductive effects we can see results from this polar bond. If we have a partial plus that can attract the partial negative, that's going to stabilize this species compared to something like this or this, where you don't have any polar bonds in the vicinity of that negative charge. This will be our second strongest acid. And then we say, well, there aren't any additional attractive inductive forces, but look at this. We have a bulky substituent here that has a bunch of bonds. If you have a bunch of branches which are made of bonds, which are electrons, those will repel negative charge. That's going to be our weakest acid due to a repulsive inductive force. And then finally, the third strongest of the acids will be this unsubstituted A ring with just the OH. Another context in which we can apply our knowledge of the relative stability of anions is in predicting the direction of equilibrium. Remember that chemical reactions prefer or favor a side of the reaction, a side of this equilibrium, left or right, which has the greater stability of products. Now, neutral compounds tend to be pretty stable unless there's some particular other types of strain. But anions or cations are less stable than neutral compounds in general because of the excess of charge. And we can compare the stability of this hydroxide anion to the stability of this anion with an alkyl group coming off of it. Now, both of them have a minus charge on oxygen, and neither of them has any resonance, so we have to turn to inductive effects. This negative charge on oxygen and hydroxide is by a small hydrogen. Now we know that electrons repel other electrons, they repel negative charge, so that's an example of a destabilizing inductive effect. So this is a less stable anion, and the hydroxide is the more stable of the two anions. Now the equilibrium is favored in the direction that forms the more stable species, so in this case, equilibrium is favored to the right. We can apply this concept to our second problem at the bottom here, which side of this equilibrium would be favored. And again, we'll compare the anionic species, the neutral species being pretty stable. We say, well, we've got a negative charge on a carbon in one case and a negative charge on oxygen in the other case. Oxygen is much more electronegative, and electronegativity by its definition is how strongly that atom attracts electrons. Attractive forces are stabilizing. So surely this compound with a negative charge on oxygen is more stable. Not only is the negative charge on oxygen, but it also has some resonance stabilization by merit of being beside a pi-bonded species, and you could draw delocalization around the ring. Because the more stable species lie on the left, this equilibrium would lie to the left. This reaction would not proceed in the forward direction towards the right at all. Now let's look at some cations. In this course, we're going to focus a lot on compounds where the positive charge is on carbon, these carbocations. So this problem deals with those types of species. When you're looking at anions or cations or radicals, you must consider whether or not there is resonance and consider both resonance contributors in your attempt to assess the relative stability of the species. If your charged group, in this case the cation, is beside an atom with a pi bond, you know that there will be resonance because you're allowed to move pi bonds and lone pairs around in drawing different resonance contributors. Electrons move towards positive charges. So in all these cases where the positive charge is adjacent to a pi bonded atom, you should be able to have some type of resonance. This carbocation in the third example is not beside any atoms that have pi bonds or lone pairs, so you can't draw any additional resonance contributors. So there's no resonance here. This positive charge on the far right species does, however, sit beside a pi bonded atom. You can draw another resonance contributor. So if you fill in the other resonance contributors, we have these species. So now we fill out underneath each of these species which parts of its structure might contribute to our ability to rank the stability. So, for example, in this first case, you start off with a primary cation. That positive charge on the carbon that has one carbon on it is primary. It has resonance where it also moves to a primary site. So I would write primary resonance to primary. The second species starts off being a secondary carbocation, and then it has resonance to another contributor that's primary. So its resonance contributor of secondary and its resonance contributor of primary. The hybrid would have some positive charge character on a secondary and a primary site. Now, this third species is a tertiary carbocation that's more stable than a primary or secondary, but there's no resonance. Finally, this last one has a tertiary site with resonance to a secondary site. That's clearly going to be our most stable species. Our least stable species would be the primary with resonance to primary. These other two, a secondary with resonance and a tertiary without resonance, are about the same as each other. So they're approximately tied. You could probably figure out which was more stable if you did some studies, but just knowing what we know from the primer, we would say these are approximately tied for 2 and 3. A similar approach would be taken with radical species in attempting to figure out their relatives. No resonance in the cases where the unpaired electron is adjacent to sites that do not have pi bonds. And in this case, there is pi bond in the molecule, but it's not right adjacent to the radical site. So again, no resonance here either. And now we can fill in the aspects of the species: primary, secondary. This is a secondary radical that has resonance to the additional resonance contributor. Looks like this, where it becomes primary. So secondary with resonance to primary. This is primary with resonance to the other resonance contributor, which is also primary. So now we need to rank these. Well, in the primer we learned that resonance is much more stabilizing for radicals than it is for carbocations. So secondary with resonance, even to primary, is going to be more stable than tertiary. This is our most stable species. The next most stable would be the tertiary. Primary with resonance would be the next most stable. Primary without resonance is going to be our least stable. This next problem asks us to draw a qualitative reaction coordinate diagram for each of these potential reactions. The first thing we have to do is set up our axes. Regardless of how the energy changes in the course of this reaction, we have a reaction coordinate. Remembering that on the left are the starting materials, on the right are the products. And then we have energy on the y-axis, the vertical axis. Higher in energy is less stable. So one thing we have to figure out to do this properly is to figure out whether the starting material side or the product side has the more stable species. And again, we're going to focus on the ionic species because the neutral species are relatively stable. The greatest contribution to the energetics is going to be from the ionic species. So we have bromide. This is a very big atom. And oxygen is much smaller. The bromide anion is more stable. So in this case, we have a case where you have more stable starting materials going to make less stable products. This is not a reaction that would be particularly favorable. It wouldn't be a reaction to try to do in a practical sense. You'd have to start with some starting materials at this energy and go to a much higher energy species at the end. You'd have to have some energy barrier to accomplish that. And it's as simple as that, figuring out which side is more stable and adjusting the energies accordingly. Now, the second example at the bottom is a little more complicated. You have the same setup for the reaction coordinate and the energy, but now you have two steps. So you start off with a neutral compound, and it undergoes a heterolysis to two ionic species. That's going to be a rather large jump in energy. So if we start this off at some starting energy, this is going to be higher. And then how does the energy change in the second step? We're reacting these two ionic species then with water, and you get two neutral species, so it becomes lower again. So you're going to start off here. You're going to have a large energy jump to get to what I'm going to call step 2, or the second set of species we encounter. And then we have a smaller energy jump to go to a lower energy where we have neutral compounds. Sometimes, rather than being asked to draw a reaction coordinate diagram, you might be shown some reaction coordinate diagrams and try to get some information from those. In this case, they're asking us which product is formed fastest, which reaction is most spontaneous, and which is most thermodynamically favorable. So let's start off with the fastest. The fastest reaction is identified by taking the starting material and seeing how much energy of activation do I need to get each of those reactions to go. The higher that is, the slower it will be. EA is the energy of activation. The higher it is, the slower it is. It takes more energy to get it going, it'll be a slower reaction. And that leads to product A. So that's going to be the fastest. The slowest will be the one with the highest energy of activation, which they didn't ask us about, but we might as well fill that in. That's your slowest. Now, the next two parts of the question, this is almost a trick question, because most spontaneous and thermodynamically most favorable, those mean the same thing. It just means which of these reactions leads to the greatest energy gain overall. It's not about how high the hill is to get the reaction started. It's about the starting point and the ending point. So we're only looking at the difference between the product and the reactant. So for product C, we gain the most energy. Product B has intermediate, and A has the least energy gained. So the most favorable, the most spontaneous is the one that gives you the most energy back. You gain the greatest energy, the greatest stability in doing the reaction. This is going to be your most thermodynamically favorable. It's also the most spontaneous.